This webinar shows how to connect outputs from injection molding software to a stress analysis. Specifically, we'll have weld line locations weaken plastic in the structural analysis and see resulting material failures. I'm Shivani Patel, and I've been working with SOLIDWORKS and the simulation suite for over 10 years. With GoEngineer, I've spent majority of my time working with customers in the oil and gas, electronics, and medical industries.
And I am Jeff Lendermon, a senior specialist with GoEngineer. I have over 30 years experience in the injection molding industry, and my focus is on injection molding simulation, as well as other SOLIDWORKS and Dassault Systems tools.
Dassault Systems and GoEngineer are partners, where Dassault develops the tools and GoEngineer supports the user base. Dassault has a wide range of brands and technologies that it has developed, which fall into these 5 categories. In order to show this weld line integrity analysis, we're using technology from SOLIDWORKS and Simulia brands and connecting them via the 3D Experience platform. Let's take a look at the part file we're using for this analysis process.
Right. This part, imagine like a fluid power port in a pressure washer situation where you're seeing a high PSI of water going through these plastic parts that are connecting these things together. And what we're looking at in the injection molding process is when you're molding around the core, typically you're going to get some sort of weld line. A lot of people look at weld lines cosmetically, but there's also some issue with the integrity of the weld line. How strong is it going to be? Over time, will this weld line fail? So having the ability to actually look at your injection molding simulation and see where a weld line is going to be, and then we can actually take that data and input it into FEA analysis and actually interrogate the integrity of our weld line, right? It's a question that's come up to me over the years many times. I've been in the injection molding industry over 30 years. I've seen this. I've been asked this many times. Like, how do we know our weld line is strong? When we talk about weld lines and we're looking at them on the analysis, right, we have a weld line angle is what shows up for our weld line. So anything like less than 135 degrees, that angle is how your flow front comes together for the weld line. So the more direct face-to-face it comes together with no angle, then you're going to have less integrity, right? Your polymers are not going to interlace and connect the way they should under the heat. They're going to be more of just a blunt face-to-face hit. So that's part of why you see weld lines as a cosmetic thing on a part. You don't want it. You can see where that line is, where those two flow fronts come together. So I think on the structural side, you can probably talk about a little bit about the strength reduction and that type of thing.
Right. So like Jeff was saying, like we want to avoid those weld lines. And you could see in the previous slide how the tool will help us predict where the weld lines are. What I'll be able to show you guys in my section of the presentation is, okay, how do I take that mapped weld line, bring it into a structural study, and apply various reduction factors for how is the strength affected in the areas of the weld. We can put in that material data and then see the result of our stress studies. So we'll be able to see a little bit of how to input this type of stuff and get results in my section. But Jeff will start us off with running the injection molding analysis.
So there's different ways we can start. Since we are SOLIDWORKS users, and SOLIDWORKS is integrated with the 3D Experience platform, we have options on how we're getting the product into that. We can import directly into 3D Experience, or I can actually utilize the PLM side of the 3D Experience platform from SOLIDWORKS, and all I have to do is save this model into the platform. I can even select the compass here to access different roles. In this case, I can just access my roles. I can click on plastic injection. Now I'm in the plastic injection simulation role. So that is one of the many roles in the platform. The role that Shivani will be using has an app that also is in the system platform. But really, it's easy to start up and save and learn as well. There's an assistant where it actually tells us what we need to do. So I have my part here. It tells me I must select at least one plastic part, assign my materials, and process settings. So we can run through the assistant over here, or I can do the same type of things down here under my setup. So the first thing, my contributing parts, I can click on that. Right click on my part, tell it this is my plastic. Notice I have options for hot runners, cold runners, part inserts, coolant, which are cooling channels, or mold inserts. But we're just basically looking at the flow, the filling of this part. So I'm going to do just for the single part. Next step, we assign our material. So there's a material palette, the material palette for the injection molding, and the FEA simulation are all part of the platform. They're tied together. There's one specifically for injection molding, but we're able to actually pull that out. If we look all of these different plastics, there's close to 4,000 different plastics in the database. The So research and development team getting this data from the material manufacturers. So if I want to search for a particular one, Polypro, Himont, Profax, I can select that material, simply drag it and drop it on my part. Then I'm telling it, okay, I'm applying that to the fluid connector. So after we assign our material, next step, we're going to come in and add some settings. So melt temperature, material set temperatures, ejection temperatures, all of those things are based on our material. We can do that as well. Then we only have to add our conditions. So our injection location is one of those things. I can choose a face. I have a split line on my model that's going to allow me to choose that face. I could actually grab points or anything like that. And then beyond that, if we watch my assistant over here, I'm actually ready to simulate at this point. There are additional things we can do with mesh. I can look at my mesh part manager. Maybe I want to make my mesh a little bit finer than what that is. We can do that as well. I can come in and add mesh refinement to certain areas. I'm going to go ahead and mesh this. I think 1.31 is what we ended up using for everything. So then we see the mesh on our model. Then all I have to come over to my results and I can run the simulation. When I do this, we have the option of choosing how much of my CPU that I'm using. So I have 8-core processor. I can tell it I'm going to use all 8. I can also choose if I want to run this in the cloud as well. So we're not utilizing my CPU. We're going to use the CPU cloud compute that we have on the platform, which Shivani, I think, might talk a little bit more about that on her side. I'm going to go ahead and go to my results, since I already had one run, and then we can see some of the results that we can get in there. I'm going to activate the results. In this case, I've run filling simulation, pack and cool simulation, and warp simulation. If anybody's familiar with the SOLIDWORKS plastics package that we have, there's Plastic Standard, Pro, and Premium. This doesn't have different levels of package. You get all of the capabilities of Premium, basically. They're both based on SIMPOE anyway, so a lot of the calculations and all of that are the same behind them. Right now I have it set up to my weld line, so we see the weld line on the side of the part, exactly how we were talking about before. All my different results that I have here, I can go to my fill time so we can actually see how it's filling and wrapping around the part. Slow that down a little bit. And we can see it's creating this weld line. So different areas, if it zips up like a zipper, it's usually not too awful, but when you have an area that just butts straight head to head on each other, then we start looking at problems. So from that point, all I have to do is tell Shivani, it's like, hey, can you run an FEA simulation on this part? I can send her the information on the weld lines, give her access to the part, and then she can take over from it.
Yeah, sounds good. Cool. I didn't see any questions come in about the plastic injection just yet, so I'll go ahead and start with the structural side. So the weld lines that Jeff was able to generate, you kind of saw the way the fill analysis worked, and this is the type of output that plastics injection molding would give us. A range of degrees for how those flow fronts came together. Now, getting into a structural study, what we're going to do is essentially bring this into a structural analysis. And I'll get to show you some of the setup there, but I won't show every pick and click. Kind of thing one, you're going to want to mesh the file. So this is the type of tetrahedral mesh I used for the part. And then we get into that plastic material. It's really the first part of the setup. At the beginning, we mentioned weld lines and maybe a little bit of fiber orientation of things we can bring in from the plastics injection molding setup, from the plastic itself. So the two types of orientation that I've noticed with some of these plastic parts that we're bringing in, one type of thing is the fiber reinforcement, which we can start bringing in some of that orientation data kind of here in our material database. Another kind of common thing I've seen is orthotropic or transversely isotropic type material properties kind of embedded also into the behavior. So the material that we're using today is this type of transversely isotropic elastic modulus plastic. Bringing in something like that does require us to essentially specify the orientation, the XYZ, of that material. And rather than using a global orientation, we will use what's imported from plastics. So I'll show you a little bit of how to do that. So if we take a look at this structural study, I've got some basic stuff kind of already set up, like the study's already begun. But to get going with the material orientation, this is kind of like the first step of the analysis. I would say, hey, in my solid part file, using this material that Jeff ran in the plastic study, I'm going to go to material orientation, specify, and choose to import it instead of using what would have been the default, the global. Typically, this will come in blank. And so what you'll do is you'll hit the search, navigate over to the plastics injection analysis, and click this top icon in the tree. And that imports it into the study. So give that a click. It would import the results in. We would kind of see these drop down start to populate. And from there, I would then choose, what moment in time I'm getting that material orientation from. So the fill simulation, for example. The whole model, and I'm bringing in that material orientation. I hit OK, and that is how we're bringing in that material orientation data. All right. Kind of next piece there. The rest of the structural setup. The faces you see selected here are the areas that I locked down to say, hey, they basically cannot move. I'm saying the bottom is kind of clamped to something else. In areas of the threads where something else might be threaded in, those are not able to move very much. I didn't apply a preload to those threads. They're just held in place. And the next step, I apply a pressure onto the internal faces of this port. That pressure, it's going to range from about 0 to just about 3,000 psi over about 0.8 to 0.9 milliseconds. Okay, 0.9 milliseconds is what we get up to. So I'm ranging about 3,000 psi, about 0.9 milliseconds. Before I just go hit run, we do need to get into importing the weld line and that material data into it. And there's two pieces to doing this. The first is this initial field, and the second is field variable. So I'll focus on initial field. In my structural setup, where I would have already done the kind of clamped faces and the pressures, we then get into initial field. This is an initial condition. I'm going to import something across the entire volume. I'll select it for the entire body. We'll talk about the number in a second, but for now I'm going to leave it on its default of 1. And instead of magnitude where I type in a number, I say it's external, I'm going to import it. And this should start to look familiar. It's exactly the way I imported the material data from earlier, right? I click search, I click the tab, and I click top of the tree. At that point, I want to bring in the weld line information, which is going to be from the fill simulation Jeff ran. Do the end of the analysis. And in my field tab, I scroll on down to weld line. But while I'm here, you can see all the other types of things I could potentially import across the file, but the weld line is. So I go ahead and select that, and that begins to bring in the weld line information. But really, to finish this up, to really do this properly, that's not enough. We need to start talking about this field variable. A field variable is essentially a custom material property. Let me give you some examples. So this field variable, again, a custom material property. When I'm in the material database, whatever I'm clicking on, look for like this section of it where it will say number of field variables. Essentially, for this example of density, I can tick that number from 0 to 1, and it will add the column where I can then have whatever my parameter is changing depending on that field variable. And in this kind of random example, I'm saying, hey, when the field variable goes from point 1 to point 2, my density gets greater and greater. So in this very simple case, you can kind of think of it as like an XY curve, right? As this changes along the x-axis, the y column changes, right? In a simplistic form, this is what the field variable additional column is doing, right? With that kind of example case. But we want to do this for something a little more complex than density. We want to do this for kind of the strength of this file, which there's a lot of different places I could have material properties vary with the weld line strength, that field variable. So I'm going to pull up the material palette. This is our material database. It has some predefined materials that come with 3D Experience platform. The plastics materials that we are using are part of that default database. But you can also import, of course, materials from your SOLIDWORKS libraries or your own custom materials as well. So this is the one Jeff used in his plastics presentation. So I'll go ahead and pop that up. And I need to make some modifications for this to now vary with that field variable. So for example, I could say that the damage, when something breaks, have that occur earlier for the case of the field variables. So right now what I'm saying is, hey, when there's no weld line, this is the way that this plastic fractures after this type of strain. And then what I could then do is say, hey, in the worst case area of the welds, where this is like at the worst 90 degree or 0 angle, perhaps this fracture strain goes down to something quite small, like 0.02. I could say my stress to axiality is 0 or something. So you can see me start to build up this plot where I say, hey, where along this problematic weld line am I? What is that angle? What is the worst case degree of that weld? And how is the fracture in those areas, for example? So you put in that material data, and that affects the structural data in the areas of the weld in a different way, right? Now I'm using this kind of 0 to 1 scale. How did I know to pick 0 and 1 and not like 135 degrees or 0 degrees? Like, how come I wasn't choosing degrees? I was choosing these kind of scalar numbers. And this comes from being able to view what the field variable is being imported like from the plastics database. So I'm able to view that by creating a custom output. So I can do that here. I'll edit the one I already have and say, I would like to also output a visual result for field variables, anything that I'm bringing in from the plastics analysis. Okay. now show you a little bit what that looks like. So once you run a study with that field variable plot, we can generate something like this. Compare this against the weld line data Jeff produced, where the red areas were closer to the higher degrees, the 135s, the 145s, and the lower degrees, the blues here, were closer to zero, the flat flow fronts. And as we look at that compared to the field variables, well, my higher numbers, my 1s and 1.2s, are in the areas of those low degrees, those zeros and 90s. The zeros, essentially, are where the worst numbers are in this field variable. And then the better interactions, the 135 degrees, the 45 degrees, those basically don't show up here in the field variable plots. Okay? So that's part of what the visual output I'm getting, but that's also why I'm using that scale of 0 to 1 as I was putting in my custom material properties. All right. So once I put in that little bit of damage modeling, and those field variables and the material properties, that's enough to get this running. So I did go ahead and give that a run, applying that pressure, and with that damage model, we see elements delete as that particular fracture strain is obtained. So we get to about 1250 psi before we start seeing those elements begin to delete. So a little bit into the plastic portion of that curve. And so we see a crack essentially and what would be failure in the field, right? So really then the question is, can we find a way to improve this and maybe move the weld line to a better location? And that's really where I would go to Jeff to tell me what a better location would be.
So the more obvious answer, in the bottom center of the part, if you're able to gate there, then you're going to get a better fill. And it just depends on how you want to build the mold and everything. But just to show the effect, we want to move our gate location to the bottom center of the part. It's as simple as opening up that study again, starting a new study, picking a new point for the injection location, and then you're running another study. You're going to get more results from the weld line. So we went ahead and ran it, and we've got a little animation of showing it filling. So now it's filling from the bottom up. That area where the weld lines were no longer there because we're not wrapping around that big core. There's other weld lines that are coming into the part in different areas, but they're also not as prominent, right?
Yeah, not as prominent and not as the critical pressure areas that are going to be seeing a lot of expansion.
Right.
Because of that pressure. Like these areas just don't see as much of that expansion. So fortunately, I ran it with the same material data, but I import these weld lines and there's that kind of initial field variable data, and we give that a run. And it clearly gets all the way through into that 3000 psi without failure. So yeah, by moving those weld lines, we were able to allow this port to expand without a total catastrophic failure.
Thank you for your time and attention into this quick dive on how to connect plastics injection molding results with the ABAQUS solver. The 3D Experience platform's universal file type is opening doors between physics that typically required a far more complex series of steps to connect. Tune in to future webinars or reach out to us at GoEngineer for other efficient developments with 3D Experience.